Congrats on the first. Enjoy playing games with your friends. The best is yet to come. That's good fortune. The best physics is yet to come. It's coming very soon, though. Okay. I just want to take a second to make sure my stream is working okay, and then I'll jump on the voice call. I had to mess with some of my settings for the review-a-thon, and I think I put them back okay. Yeah. Okay. I guess let's hop into voice then. Hello, hello.
Hey, Don.
How's it going?
Pretty good. How are you?
Pretty good too. Do you feel ready?
No, do you?
Me neither.
No, I don't. I really don't, but we'll see how we do.
Yeah. Hey, Skirt. Sorry, what?
Sorry, that's my Twitch echoing back. I just
Okay.
muted it. Yep.
So yeah, I don't know how much like studying you did. I just read the chapter summaries for like maybe chapters 5 to like 9 of the Purcell book. I don't know if that's going to be enough though.
You're probably doing better than me. I went back to the MIT open courseware stuff, and I started from the start. I only got as far as Gauss's law, so I think if we were doing the first exam again, I'd be doing fine. But I haven't done any review for what's probbe on this one.
Yeah, I don't know what to expect.
I figured you could carry me. That's okay.
God,
right?
I was hoping you would carry me.
Oh no. All right.
Yeah, at least when I saw Zach doing the first midterm, it seemed pretty doable. I feel like I remember what I assume will be on a second midterm a lot worse, but it'll still be interesting.
Yeah, it'll be interesting.
Yeah. So I got it open here. I guess I'm going to start scrolling down and we can pull the first problem in if you're ready.
Yeah, sorry, I'm somehow on the wrong Excalibur. Let me go
Oh,
back
okay.
and find the right one. Oh yeah, sorry, I'm clicking on Excalibur from the wrong Discord. Here we go. I think I'm, yeah. Am I back? Yes, I'm back. Okay.
Syntax. Oh, it's probably too late. That sucks though. I hope you hear back soon. Wait, so you ready now, femvox?
Yeah.
Okay. Let's get the first question in here. Well, yeah, we already got something about the B field.
So how strictly are we doing that? I mean, we're already double teaming the exam, so I guess we're already cheating, you know.
Oh, I mean, so the thing before to say it's open book. They say OpenStax, but I want to use Purcell.
Oh, really? It's open book.
Yeah.
Handwritten annotations on the pages of that book.
Which is kind of interesting, but not like printouts or other pieces of paper. But yeah, so I figured chat would probably chime in too, but
yeah,
I don't think that's a big deal.
Syntax is already calling the physics police on us.
Yeah. Academic integrity used to be a thing. Not anymore. Now with Chat GPT. Okay. Wait, what am I doing? I'm not used to my tablet controls for Excalibur, so I have to like relearn them. Hey Rex. Okay, so a charged particle moves with constant velocity v through a uniform region, or through a region of uniform non-zero electric field E, and uniform non-zero magnetic field B. Which of the following is true? Okay. You can see the question I just pasted on the screen, right?
Yeah, I can see it on the stream and I can see it on the Excalibur as well.
Okay, cool.
I think I'm with you. So we got constant velocity, so we got no acceleration. So that's got to be telling us something. So what about, can we use like the Lorentz force law maybe? Is that the way to get this one?
I guess so. A charged particle. Yeah, so
I remember F equals QE. I remember that from electrostatics, but in dynamics, you got to have some magnetic field, don't you? Like V cross B or something.
yeah, Q V cross B.
Okay, so maybe this will get us there.
And so yeah, in our case, F is 0.
So E plus V cross B is 0.
Yeah, we can get rid of the Q's entirely, can't we? Wait. Oh, that's the eraser. Okay. Oh my god, why do I have my hotkey set up like that? Okay. And so
Non-zero magnetic field, non-zero electric field. Okay, so he's made sure we know that they're all both non-zero.
yeah.
Because otherwise we could probably cheat and just say there's no fields. Take the easy way out.
Mm-hmm. So I'm trying to figure out what this cross product is doing here.
Yeah.
Um, or maybe it's one of those where we should go through the options and try to eliminate them.
Yeah.
E must be parallel to B.
So what if B was going this way?
Uh,
Then there'd be a. I have a feeling like they're both going to give you a force, and the forces are going to have to cancel, right?
yeah.
Oh yeah, because the way we've set it up now, this is definitely a field. This is non-zero, so that means this has to be. Yeah, you've already shown it, right? So this has to be the negative of this. Okay, so so V cross B. Okay, so now we can use the right hand rule. So right, so V cross B
I
would
just
be
doing it with my hand. I think it's coming out of the page, the right hand rule.
towards us. Yeah.
I forget how you do that. Is it an open circle?
Yeah, like a dot,
Close
like
okay.
an arrowhead coming at you.
And so that means E would have to counteract that, and E behaves. So E would be going into the page.
Yeah.
Um,
So
I
wouldn't
think
it
it's an
be
X.
Oh, well, this is sneaky. I wanted to say E and B were at right angles, but that's not a choice.
That's what I wanted to do too, because I was thinking of like a
Oh,
light or a light wave, whatever.
yeah.
Ooh, wait.
Oh, well,
So
maybe is this it?
yeah. Because that's the only way. Because well, wait.
Yeah,
Uniform.
look at these 5 and look at what you've set up. I mean, C is the only one that works, right? With what you've set up in the picture, I think.
Yeah, because the force from B is always perpendicular to V. So E has to counter that, so it has to also be perpendicular.
Nice.
Okay, cool.
Nice.
Wait.
All right, one down.
Not so bad. That's probably just the confidence builder one, but
That's
you
probably
know.
yeah, I know. That's the easy one, right? That was the easy one.
Oh yeah, this one looks. There's a lot more symbols in number 2. I guess I'll go downwards. Okay. Maybe give it a bit more room. Okay. Finite wire lies on the y-axis in a right-handed coordinate system, carries a current I from y equals minus a to y equals plus a, which of the following is a correct integral expression of the magnetic field B L0 produced by the wire at the point xy equals L0 on the positive x-axis. Take which? Yes, second year uni.
So this is like minus A to A.
Mm-hmm.
And we're going over here somewhere, L. So there's a wire. Let's say this is the wire.
Thanks for the work, famished. BL0.
Um,
So we can
what's
eliminate a
this
lot of
called?
these
Is
just
this like
figuring out the
Ampere? This is
direction.
like Ampere's law or something, isn't it?
Yeah. Oh, and Dr. Cook's here.
Uh-oh.
Ampere's law. I do it off the top of my. I guess it's open book, so we can just like look at it. But like, I think it's the integral around a closed loop b dot ds equal to mu naught I enclosed.
Ah,
I want to say. Let's confirm.
okay. And this is
Hey, I got it.
not, and that's a line integral, right?
Yes.
Okay.
I was about to say that there's like a known thing for the magnetic field due to a wire, but they are asking for integral expression, so I guess we don't use that. But I think that's Bill.
Oh yeah, F equals Bill.
Oh, it's a finite wire, so it's not super useful. Hmm.
How are we going to construct one of these integrals? L squared plus y squared dy.
Here's a lot
So
doesn't.
L squared plus y squared is like a distance to a point, isn't it? As we move a point along the wire.
Yeah. Okay, and so we have 2 votes against Ampere's law, and in part because the current is discontinuous at minus a and plus a. Ampere's law requires a steady current. Uh, I I think we're okay with hints because it's open book anyway, and it's hard to not have hints when you stream it. So I guess like the first thing I'm looking at is which one of these do we want? Wait, how does the right hand rule? It's tangential.
We got x's and z's in front.
I'm doing the.
Yeah, wait a second. We got z's versus x's, right? I mean, I feel like one of those could be ruled out pretty quickly.
I think uh, it's minus z direction. Just
Y, z. Yes, I agree too. So
okay.
it's one of these first ones, isn't it?
Yes.
Because how's it work? You put your thumb in the direction of the current, don't you? So you
Mm-hmm.
put your thumb in the direction of the current, and your fingers wrap around in the direction of the magnetic field it produces. Oops.
Yeah.
Yeah, so this magnetic field here should be going right into the page, shouldn't it? At that point.
Mm-hmm.
Okay, so
It was in the x direction. It would have a divergence. Oh, interesting. I didn't think about it like that.
the only question is do we have an L here or a Y here?
Right.
L is this distance, Y is this distance. So which component are we looking at to construct this magnetic field?
Is this Biot-Savart? Or how do you say it? I think it
might be, yeah.
is.
Yeah, it might be.
Okay, I'll screenshot it and bring it in. Okay.
Yeah, look at that. Beautiful. DL cross R. So the DL should be in the DL cross with R. Yeah, how does that work? So the DL goes along the wire, doesn't it? This little DL here.
Yeah.
Okay.
And then R. Like for the blue line that you drew, I think R is like that? Or.
Oh, our hat, yes. That R hat would be out here, wouldn't it?
Yeah, does that give us the thing we want when we cross it? I guess it would.
The DL would be going this way. Well,
Okay. And so I would imagine we're getting... Okay,
so
yeah.
if this is theta. This is theta. Oh no, my phone's ringing. Sorry.
Oh no. Ivan, magnets, how do they work? Exactly. Hope you're doing well, Ivan. Hello, hello. I think Femvox might be having tech issues.
Sorry about that.
Oh, welcome back. Ivan says hi.
Ivan, hi.
Um,
Yeah, I remember DL was like a little vector in the distance of the current, right? The current flow through the wire.
yes, it is. The DL travels along the wire. In little chunks. ILR. Trying to figure out how we get anything in the numerator right now. Like, what's less than L or Y in particular?
It's either L over L squared. Oh, it's either either the cosine or the sine of this triangle, isn't it? It's either like this over this, or it's this over this. But which? Oh, it'd be. Well, wait. If it's a cross
Oh,
product,
because the cross. Oh, it's sine, I
yeah.
guess. Yeah. Right?
Oh.
Because A cross B magnitude.
Yeah, it's the sine of the angle, right?
Is it the
And
same
this thing is
theta? I guess so.
this thing's a unit vector. So it should be L then, is that right? So
Yeah, I guess that's leading us towards A.
oh. So what if we let L go to 0? I mean, if we let L go to 0, this is all 0, isn't it? So would the magnetic field be 0 at the point in the middle here?
That's a good question. The alternative, if L is 0, we would just get a constant magnetic field. Or would we? It'd be Y? No, it wouldn't be constant. Or, sorry, it's constant at that point, no matter what. I was thinking of what happens inside there. I thought the Y's would cancel, but they don't.
I'm leaning towards A, but I'm not sure.
Same. I'm okay with just putting A and moving on, I think. I think the only thing that could be sabotaging us is if the theta, if we're taking the wrong theta, which would mean it's kind of like we're taking the cosine. I don't think we are.
I mean, from your formula here for BS of R, I mean, I think it's this. Is this did the picture I drew here? Does that sort of correspond with our formula?
I think so. So
yeah, I think so.
I feel good about that. Okay. Let's bring in number 3. I see farads.
Nice.
Okay. A 3 microfarad capacitor and a 6 microfarad capacitor are connected in series with a 12-volt battery. What is the resulting voltage across the 3 microfarad capacitor?
Oh, nice. I think I
Uh,
know this one.
isn't it like V equals QC or I've or it's something like that.
I think when you got capacitors in series, you got to use the product over the product over the sum to get the equivalent capacitance. But maybe we don't have to do that because we just want voltage across the one of them.
uh, what's the symbol for a battery again? Hey Daniel.
A battery's like this.
Oh, with one bigger than okay, yeah, and then a capacitor they're equal size. Okay,
Yeah.
I just wanted to actually like draw it. It's not all that important, but 12V. I don't know if the order of the capacitors matters. I doubt it.
Nah. So if you got 3 and 6, I think it's 3 times 6 over 3 plus 6, I think, which should be 2 microfarads equivalent. When they're in series, they have the same charge, don't they? So whatever charge gets pushed to here also gets pushed to here.
Oh, that makes sense. Okay.
Yeah. And okay. Now, what did you say it was? Q equals CV, or
I need to
always
go back and look at it.
yeah. Um, we should be able to work that out from units, shouldn't we? Coulombs
Capacitance
and
Q
volts.
equals CV. What is wait Q though? Oh, it's charge, right?
Q is the charge, yeah.
Okay.
So it's the same. Okay, so C1 V1 is C2 V2.
So charge
Okay,
is
and
the
we know
same. Okay.
yeah, and we know V1 plus V2 is 12. That's what we know.
Right. Okay.
Yeah.
Now we're talking.
So
So
3 and 6. So 3. So what is it? Can we do it by inspection? One of them's twice the other one, and they add to 12. So it's got to be 3 and no, it's got to be 4 and 8, doesn't it? 4 volts and 8 volts.
you're quicker than I am with that. I would need to
Yeah,
write it
three
out.
eighths and 6 fours.
3/8 and 6/4. That's way too small to add up to 12, though, isn't it?
Well, the 8 plus the 4 gives us the 12. And then 3/8 is the same as 6 times
Oh,
4
that's
over
what you're,
here.
okay. Oh, nice. Oh, nice. Okay. And we wanted if wait, if V1 is 8, is that the 6 microfarad?
Let's see. So 24 microcoulombs, I guess, is what this means was stored on each capacitor, right? I think this right here is the answer. Maybe 8 volts across the 3 microfarad.
Uh
Let's see if it makes sense.
oh, I guess yeah, for fixed charge, higher capacitance is lower voltage. So we do want the smaller or the bigger one. Because we're asking about the 3 microfarad.
Yeah.
Okay, yeah. So we want D.
Nice.
Okay. So far, so good, I
Oh,
feel
good.
like.
Yeah.
Only 3 problems in. A long straight wire carries current I into the page, uniformly distributed over its cross-section of radius A as shown below. The wedge-shaped path L has radius R greater than A and subtends an angle theta. What is a magnetic field circulation, the integral B dot dl around the directed loop L?
Oh.
I would think that the straight R paths are gonna cancel. I
Yeah.
hope.
Yeah. That feels right. And then L is like an arc of a full circle, isn't it? So
It's probably just like some, like, yeah, like the magnetic field of the full circle divided by the angle or something.
hmm.
I don't know if any of these options match that obviously, though. Maybe E and B do. Uh,
So what's mu naught
I
I
don't know.
over 4 pi again?
Sure, I think A and B are definitely wrong. Uh,
Because from your Biot-Savart law before, it had mu naught times I over 4 pi was kind of like a factor in front of
yeah.
the differential or whatever. So is that going around like the whole circle, maybe? Maybe not.
Hmm.
Ah.
I'm also curious about this. Like, the I in Biot-Savart might not be the I that we're given in the problem.
No, you know what? Because look, the I is uniform through the whole circle, isn't it? That's what he told us. But we're
Yeah.
taking like this slice of it. So we're not taking the whole I, we're taking just part of it.
Mm-hmm. It would be I enclosed is equal to like it's probably just theta over 2 pi.
Yeah. Squared over R squared. He gave us 6 choices and they're in pairs of like plus or minus.
Mm-hmm. And I think B and E seem wrong, because if theta equals 2 pi, there's no magnetic field. Oh wait, this is asking about the circulation, the result of the line integral. I feel like it should be non-zero if theta equals 2 pi, though. Because that will be enclosing, it should be equal to just I.
If we ran around the whole circle like this?
Yeah. Oh yeah, okay. Because of Ampere's law that I wanted to use, we should recover mu naught I if theta equals 2 pi.
Ampere's law, yeah. How did that
I
work
think we are
again?
allowed to use it now. If we did do it around the entire thing.
So Ampere's law is to magnetic fields kind of like Gauss's law to electric fields.
Exactly, yeah.
Oh, this is the one you just told me about 10 minutes ago and I already forgot it. Okay.
Yeah, and although it wasn't supposed to
Yes.
be used for that problem anyway. So I think it's immediately A or D.
Oh, this looks fantastic. Yeah, look, that's exactly what we're doing, isn't it? We're integrating magnetic field around a line integral.
Mm-hmm.
Okay. And so if our contour went right around the whole thing, that whole circle, it would be mu naught times I.
Mm-hmm.
Okay. So
And this direction is against the magnetic field. I think it should be going like the magnetic field is going the other way.
oh,
So
into the page. You're right. So is it D? Are
I'm
we
leaning
leaning this
towards
way?
D. I would like to eliminate F. Like, what is wrong with F? Should it
What would it have to do with this ratio between the A and the R?
A is a constant. As R gets very large, it would drop off to 0.
Is that what it's supposed to do? I don't think that's supposed to do that, right? Like we can make this contour as big as we want in this law, right? And this side doesn't change.
Right.
Right? Like if we doubled R and came out here somewhere and did the same arc, shouldn't we get the same answer?
I think. um. Yeah, I want to say for the sake
Yeah.
of the result of this integral, it should be the same thing. Like magnetic field, it does drop off with like just the inverse of R or something for a wire, but we're not talking about that. We're talking about the result of that integral, which is different.
Yeah, I mean if the field might drop off, but if you go over a longer arc, right? I mean, as you go further out, it's a longer arc to integrate over. So
Yeah.
I think the circulation wouldn't change like that. Yeah, let's go with D.
Okay. And Dr. Cook sounds like he likes that. So, like, the field does drop off with 1 over R, but the circumference goes up by R, so it cancels out in the end. Okay. Noish.
Nice.
Ooh, we got some capacitors.
Hmm.
All right, 4 parallel plate capacitors, 1, 2, and 4 are shown below. The plate areas and separations are indicated in the diagram. Each capacitor is initially uncharged before a 9-volt battery begins individually charging it through a 1 kilo ohm resistor. If all 4 capacitors begin charging simultaneously, which capacitor reach voltage 3 volts across its plates first? Huh. So we've got an RC circuit.
Yes, and isn't it like tau equals RC?
Something like that, yeah. Hey, Sakna, I'm good. How
Okay,
about
and
you?
R is 1 kilo ohm for each one, but the capacitance is going to be different, isn't it?
Yeah, and we can figure that out
Here's another.
from the geometry. There's a formula.
Yeah. Yeah, there's a formula. How does it work?
Epsilon naught A over S.
Is S the same as D?
I believe so. Let me screenshot that. Hey, Freya. Thank you for the good luck.
Okay.
Yeah, I do believe S is D.
Yeah. So A to D. Oops. Two A to D. 3. Oh, wait. 3A over D over 2. That's 6 then, isn't it? 6. And this one would be 1/2. I think this one's the highest and this one's the lowest, I think.
Okay.
Capacitance, I think.
Um,
This anyway.
I agree with all this work, yeah. Oh, good luck, Sakna. I hope it pans out for you soon. I know it's tough.
So
So
time constant is RC. So if C, so And tau tells you like how much time it takes to charge to like some certain percentage of its maximum charge. So if tau is smaller, it's going to charge quicker. Yeah. So if the capacitance is smaller, it's going to charge more quickly. But wait,
we
we're not
want a
talking
certain
about
voltage.
we're talking about we're talking about 3 volts. So and it's a 9-volt battery. Okay, it's a 9-volt battery, and we want to get it to 3 volts. So we want 3 volts there.
Where does Purcell Morin do RC circuits? I remember there being a bunch about that.
I think it was much later, like chapter 8 or something.
There's AC circuits there, but oh, okay, you're right. This is for AC.
Oh.
Hmm. I wonder if he made it an exercise earlier on. Oh. Fair enough, Sakana. Sounds like a lot of work, but... For what? Sakana. Okay, sorry.
Yeah, because when it's DC, you have like you throw the switch and like here's some max Q or whatever, and it comes up like this, doesn't it? Like it's an exponential curve. Max charge.
Yeah, I'm trying
And
to
this
look at
is
the differential
2.
equation. You have V...
But if they have different capacitances, then doesn't that mean they have different like maximum storage abilities, basically? I mean, that's how it works, isn't it?
Yeah.
Yeah, we should like set up a differential equation and solve it.
Yeah, it's probably overkill for what this question is asking, but I don't know how else to do this. Do the van life? Fair enough, Sock now. Q overseas. That doesn't... I guess that's fine. So we have IR plus... I guess let me... R dq dt. Oh, wait.
Yeah.
Okay, that is what we want?
Yeah.
It's 1 over CQ is equal to just... Ooh. Oh, yeah, okay. It's equal to the batteries. 9. My Q... Oh, God. My Q's and 9s. Let's do uppercase Q, I guess. That... So, this is for the charge, though. How do we get the voltage out of this? I guess we go back to Q equals CV.
Yeah.
The equation is not dimensionally correct. Really? Did I mix up Q equals CV?
That's what we used earlier. Oh, that's a 9, Hamilton. The right hand side is
yeah, it's supposed to be a 9. That's why I switched to uppercase Q. Because we have a 9-volt battery. I could have put the fancy E. No, it's okay. It's confusing. I know. um, I I feel like we really shouldn't have to do this, but I
No, no,
guess we
no.
can solve
There's
this.
a better way to do this, isn't there? There should be a better way to do it.
It's a decaying exponential solution plus uh the particular solution would be, is it just a linear function? No, it shouldn't. Probably another exponential.
When there's 3 volts across the capacitor, then there'd be 6 volts across the resistor. And if we got 6 volts across the resistor, we can work out what the current is at that instant. Does that help at all? If we know what the current is instantaneously, that doesn't really tell us anything about how long it took to get there, does it?
Hamiltonian dynamics saying this is the way, the exponential thing. Okay. I'd almost rather just look up what the solution to an RC circuit is than actually do it. It's kind of annoying. The book doesn't list this. I assume it must be an exercise if they don't do it for you.
Okay, let's. What is this? So on my graph here, like what is this here? This is what's the long-term solution of this? If this is time, what am I trying to graph here? I think this is charge, isn't it?
Yeah, we're solving for
So
charge. Hey, Thorfinn.
so as time goes to infinity, what do I know? I know when time goes to infinity, eventually I get 9 volts on the capacitor and the current stops flowing, right? So at this point, so in my picture here, this is like 9 volts on capacitor. And so then at that
Well,
point, we can
isn't this
work
charge
out,
though?
yeah,
That's
so
the
they
charge
have
that
9 volts. And
corresponds
if
to 9 volts. Okay.
yeah, exactly, yeah. We want to find out what's the charge that corresponds to that. So, so if Q is CV, then 9 times the capacitance. So it's inversely proportional to, if V is 9, so Q over C is 9. So if I double the capacitance, I have to double the charge that I'm getting to. If I double the capacitance, I double the maximum charge that it's going to hold, right? Given that it's
Yeah.
hooked up to a 9-volt battery. And we want to get to 3, so we want to get to like 3 volts. Oh, well, wait. I think we're being silly. So
I think we are too.
if that's 9 volts, this is 3 volts. I don't think it matters. I mean, this thing looks the same
We're asking,
when you
yeah.
scale it. Well, then isn't it just this one with the lowest capacitance?
It should be either the lowest or the highest. I don't have good intuition for what capacitance actually means in for this context. Mr. Common Filter thinks the opposite, that higher capacitance is best. I don't know though.
Oh, Kalman Filter says it's 4.
Because the I don't remember what the solution looks like, but it's at least for Q, it's something like some constant e to the minus RCT, right? E to the minus RCT.
RC over T, I think.
RC over T? Oh.
Something like that, because RC has the units of time.
Oh, okay.
Or it might be T over RC even. I don't remember now.
Oh, T over RC sounds better.
Okay.
I kind of do you mind if I just look up the solution to an RC circuit? I don't want to solve a differential equation.
No, I don't mind.
Okay.
No, I don't mind.
Um.
Dr. Cook's going to take points off.
Yeah. Thorfinn says it's a capacitor with a small capacitance. So he's agreeing with what you said earlier.
Yeah, that's what I think, but it just seems counterintuitive.
Yeah.
You know, maybe if you think about it, if the plates are smaller and if they're further away, then isn't it easier for me to push charges onto them? It feels like it would be.
Smaller.
So I could.
Oh, it's like a spring, maybe, where a weaker spring is easier to press?
Yeah, easier to extend.
Yeah, or extend. Even though it stores less energy? That's where I'm getting confused, because I would think higher capacitor is, like, better in some way. But, it might be like what you're saying. It's better at storing energy, but it takes more work to actually get it there. Is this for the same type of circuit that we have? Okay.
Oh, you're on the OpenStacks? That looks cool.
LibreText.
LibreText.
I think this is what we want.
Yeah.
And so that tau is what you said it is. So if it's when we have a circuit in series, the charge is the same everywhere, like the current.
The current, yeah.
We do have an equation for current if we just take the derivative. Do we want the charge across one of the capacitors? And so we're gonna have V equals, I guess, big Q, just to not look like a 9, over C. I don't know what their epsilon is in this first one. Is that the?
Yeah, I wasn't sure what this was either.
It's just a constant, so we can probably safely ignore it for the sake of this question. Q equals C epsilon? I think that's for their voltage. What?
Hey, Slim.
Hey, Slim. Meat, that's the saddest to eat? I guess veal.
Veal. Oh, because it's just a baby.
Yeah, or I
that is
guess
kinda
lamb
silly.
would have. Yeah,
Yeah.
am I prejudiced against sheep if I think veal is sadder though? I'm doing math with better Slim. There is no better Slim.
I think what we worked out is that I was fat or slim.
Oh no.
Let's just say it's 2.
Just say it's 2.
Well, I don't know. I
I
feel
mean,
like it's 2. But somebody in chat said it was 4, right? Kalman filter. That makes me nervous.
yeah. What the thing I was just trying to work out from this equation is if I'm just going to assume that this C goes away in somehow. So if we increase C here, what happens to the graph? A higher C is a smaller coefficient in front of T, which means this exponential decay is slower. Oh god, but then it's 1 minus that.
Yeah, I think this one, when you got 1 minus e to a negative, I think it goes like this, it's like asymptotically
Yeah.
increasing
But like
until it gets to that.
I'm gonna cheat even harder and go to Desmos.
Yeah, okay.
What I want to figure out is minus x over a, and then I want to play with a and just see how it changes.
Yeah.
So if a gets higher, it gets shallower.
Yeah.
So a smaller capacitance charges faster.
Yeah, I think that's what we wanted. That's kind of what
So
I wanted to say at the start with this time constant idea.
yeah, and so that does
Because tau is the amount of time it takes to get to a certain percentage of its full charge. It's kind of like it's like an exponential. Like every time you increase by one time constant, you go up by 30% of 60% of what you got left to
okay.
get to the maximum or something like that.
I'm willing to send two. Uh,
Okay, let's do it.
I think that this agrees with what you were saying.
Decay upward. Yeah. Okay.
How much time? Okay, we're nearly an hour in. Ugh. I'd rather take more time and learn from it though, so I don't mind if we go
Yeah,
over
we're
it a
having
lot of
fun. We're
time.
having fun.
Yeah. Problem 6. Problems like this, the trick is typically tau equals RC, R is same. Yeah, that's what Thumbs was saying too, Thorfinn. Just rusty on this stuff. When two identical resistors are connected in series to a battery, the battery supplies 8 watts of power. Ooh, how much power will the same battery supply when connected to the same two resistors in parallel?
Ooh.
Okay. Uh, resistors in parallel, they're probably weaker, right? I expect this to be smaller? Or wait, well, how does that influence power, though? Ugh. So like I squared R?
8 watts. So that would mean
I
4
squared
watts.
R.
4 watts.
Or,
Yeah. V equals
wait, P equals I squared R.
P equals IV, which is I squared R. So
These are university problems, Thorfinn. We had some integration ones earlier, and we will have more.
So 2I squared R equals 8. So I squared R equals 4.
Oh, across each resistor, they dissipate the same power or whatever?
Yeah, if they're identical resistors in series like that, they should be the same amounts of power each one, right?
Okay. Oh, so maybe we find out the voltage of the battery, and then we use that to figure out the new circuit?
Yeah, we'll have to set up the new circuit. Okay, let's set up the new circuit. Oops. So we still got R and V here, but now we're going to have a different current. Let's see. So this total resistance is 2R. And what's this other one? It's
Uh,
R over 2, isn't it?
yeah, R over 2. Okay. So if we keep the voltage fixed, or yeah. Hmm. Oh, the power is also V squared over R.
Yeah.
That's probably the form that we actually want. So in the first scenario, we have 8 watts is equal to V squared over 2R.
Okay.
So V is equal to 4 root R. And then if we come down to the second circuit, P equals same voltage. I guess I didn't have to square root it, did I? $32. Does that feel good?
Tell me what this formula is again?
V squared over R.
V squared over R. So this is your V. Oh, I see. So you got your V squared from up here, 16R. Oh, I love it. I love it. Yeah, I love it. But wait, this is giving us a power, 32. Yeah, I love it, Don. Let's go with it.
Less resistance is more power. Okay. That was 6. Okay, problem 7.
So it went up by a factor of 4.
P equals IV, and I is 4 times what it was because R is a quarter. Okay, we have 2 more multiple choices, and then free response.
Same power, so 4 times the current.
We're rusty too. We studied this together like maybe 2 years ago now, but I've barely even thought about it since. Okay. A capacitor initially carries charge 600 microcoulombs. At t equals 0, the capacitor begins discharging through a constant resistor. At t equals 2 microseconds. Is that micro? No, it's not. Milliseconds.
Milliseconds.
Yeah. Capacitor is measured to carry 300 microcoulombs of charge. How much charge will the capacitor be on the capacitor at time t equals 6 milliseconds?
Oh. 600, 300, 150, 75, right?
Okay.
Right?
Are we fitting an exponential curve here?
Yeah, it's exponential, but so in 2 milliseconds it dropped by a half. Look, so every 2 milliseconds it just goes down by a half. I think it's
half-life. Okay.
Yeah.
Yeah, I like that. 75.
Nice.
Hey, Leo.
Okay, there we made up a little bit of time. We got crushed by that that other capacitance one.
Leo, folks and I are solving an E&M midterm. A few years ago, we studied through an E&M textbook together, and then Dr. Cook, who hangs out on Twitch chat, as a physics professor, and he sent us a midterm just for fun because we're nerds, so we're solving it. 2 long parallel wires carry currents of 20 amps and 10 amps in opposite directions, as shown below. Which following statements are true? Wait, no, is true. Never mind. I was about to correct Dr. Cook, but I'm wrong. People on Hinge are into E&M too. In region 1, magnetic field is everywhere into the page and never... Wait, okay, 2 wires going in opposite directions attract, don't they?
No, if they're going the same direction, they attract. Yeah.
Wait, okay, right-hand rule.
Yeah, do the right-hand rule. So, like, I think in the middle here...
Wait.
They're all going into the page, aren't they? So this would all be in.
Out.
Yeah, that seems right.
Wait, I'm doing my left hand to do the right hand rule. Femvox, I'm so rusty. Okay. I try to figure out what E&M is too in Leo's mind.
I think these are coming out because 20 stronger. And you know what? There should be some place down here where we have 0 field, shouldn't there? If there's a 20 and a 10, if I'm further from the 20, somewhere down here, there should be no magnetic field, maybe.
Sure.
Oh, maybe it's this then.
Hey, Papadoria. Uh, okay, V cross B. Open the palm in the direction
Yeah.
of V. Wait. Okay, I'm sorry. I'm so sure. What's the force on the lower wire? Oh, I'm mixing up which my V is. I guess that's my problem. The mag.
Yeah, I don't know. I don't remember. Was it F equals Bill? Is that how you find the force on the wire? I think. But
Uh,
I'm just thinking about in the regions like between the wires or outside the wires, like what's the magnetic field look like? So let's see.
yeah.
This
Hmm,
dot means it's coming out towards us,
okay.
and the cross means it's going in away from us. Oops. So double check the right hand rule and see if you agree with like what I came up with these for these. I
Uh,
think up here it's always going to be coming out because the 20's stronger than the 10, so the 20 always wins, right?
probably. Um, and then see out here the 10 wire is coming out, but the 20 wire is going in, and that's why you're saying it's possible for it to be 0.
I think so.
Thorfinn likes that. Um, what are the other options? It's possible in region 2 it's possibly 0. I think they agree in region 2, so no. Magnetic field to be 0. Probably not. Yeah, I think I like E.
Yeah, let's try it.
Okay. Why does physics be like sometimes I am the goat? Next part is what the fuck? That's physics for you. Hey, math. Oh, we're on to free response now.
That's bad news.
Yeah. Oh gosh, okay. Got a lot for number 1.
At least with multiple choice, you can kind of disguise
Your
your
ignorance?
lack of knowledge. But yeah,
Yeah.
but when it's free response, you're just out there naked,
Mm-hmm. Just floating in the breeze. It's 2 worms. You were one of them, you were the other one. I don't know, Leo. Circuit shown below consists of 4 resistors and
Ooh,
2 batteries. I can see Kirchhoff's law coming in.
it's a Wheatstone bridge. I know this guy.
Oh, okay. I remember doing a problem about these a long time ago, and you called it a Wheatstone
Okay.
bridge.
Yeah.
I remember how you do them, but all 4 resistor values are given in the table below. Left battery holds an unspecified potential difference delta V. Right battery holds a known 7V. Right
Hmm.
battery supplies energy to the circuit at a rate of 28 watts. We got power in the mix.
Hmm.
How much current runs in the right battery? Does current run left or right? Ugh. Main part you enjoy so far is
Okay, so
kinematics? I'd say keep with it, Lucas. It gets really cool.
we got to solve the circuit basically,
I guess so. So,
and we know all the resistances, but we have an unknown battery. That's interesting. But we have a power. We have a power supplied from the right battery, so that must be enough for us to get it.
that'll be great if the answer was just not enough information. I guess we have 3 loops, right? We even have a 4th one. I don't know if
Yeah.
the 4th one gives you anything unique, though. It has no voltage source on its... Well, I don't know. I don't know how that 4th loop works, if it does work.
1 ohm, 1 ohm, 1 ohm, and 3 ohms.
And that's the R2. That can feel empty. I agree sometimes, Lucas. So I just start randomly defining positive directions. Sorry, what?
So if we know the right battery supplies energy at a rate of 28 watts. Oh, actually, and we know the potential difference. So that means we can find the current, doesn't it? So actually, right away, we can work out what's this current here in the middle.
Can we?
Yeah, because we got the 28 watts here and 7 volts. And it's P equals IV, I think.
Yes.
So there must be 4. So there's going to be
sure.
4. Isn't there?
I don't know if we know the direction yet, but yeah.
Well, I think the direction is. Yeah, that's a good question. I tend to screw these up all the time. I'm going to say this is the 4 amps here.
Agreed. I should probably label my units here.
Oh, that was the first question. How much current runs in the right battery? Does the current
part
run
of the first
left
question?
or find the voltage across and current through each resistor. Be sure to include direction for each current. Okay.
Orphan, I watched 2 animes. So I guess I do. Dr. Cook says 4A goes to the left. The battery supplies energy, so its lifting charge carries to higher potential. I wouldn't know that just from looking at this. I'd have to go through the system of equations. I assume it has something to do with the R2 being like the asymmetry here.
Yeah, sorry, I'm just forgetting what the symbol of a battery looks like. Yeah, the smaller side is negative, the higher side is
Yeah.
Negative, positive. Yeah, so it should go this way.
Oh, I thought. But if we flipped it, would it go the other way?
Yeah, like the symbol for the battery. That's why it has a short and a long, because it's sort of like directional.
I thought okay. I kind of assumed it was a little arbitrary. Like the current would end up flowing however the rest of the circuit was constructed. I guess I'm wrong.
No, it can, but if the question tells us that the power is being supplying energy for 28 watts, the other way it would be like,
oh, taking away,
absorbing energy,
okay,
something like that. So I see you're setting up some loops, right? So should we do some loops?
we need to find the voltage. I guess that's what B is asking us for, yeah. And I just randomly chose this direction. If you prefer the other one, I don't care. Oh no. Okay.
What does that mean?
Lucas, R is resistor. I is current. U. I don't think we have a U in this problem. There's a V, which is voltage.
So let's just start. So let's call this.
I guess we need to number the loops too, don't we? All right, and the junctions.
And this is 4 minus I1.
Hey, King Assassin.
And then this could be I2.
Is that 4 minus I1, or what is that?
Yeah, sorry, that's what I tried to write.
Oh, because you have 4 coming out. Sure, okay. I understand now.
I'll zoom in a little more.
King Assassin, this particular one is a circuit. This is E&M in general, though. We had some like here's some integrals up here that we were doing. No worries, Thorfinn. You're not excited by E&M? Unbelievable. Yeah, exactly. King Assassin, about there.
Check my currents if you want, but I think we only need to sort of pick two, and then everything else is defined in terms of those two, I think.
Yeah, I'm just checking like this cancellation. I guess when we get to this junction, the currents add. And
Yeah,
so
they're kind of both flowing into this way.
yeah, sure. I like this then.
So we want to do loop. So we want to do like the sum of the voltage drops around a loop equals 0, right?
Yeah,
Okay.
so if I number the loops like that, just arbitrarily. I guess loop 1 we got to do
So,
some addition of resistors. It's looking at the left side first. The current is
oh,
4.
sorry, you labeled that 3 already.
Oh, sorry.
Cool.
I guess that's R1 plus R3. I might be messing this up, but I'm trying to do I times R for the left side of the loop. Oh, but then we need to add them in parallel.
Are you coming around this big sort of Pac-Man shaped loop here?
Uh, yeah, but don't we need to do like both
You're
these
going.
paths at the same time, like in the same equation? Like these are basically in parallel, or do we do them separate? Maybe I got confused.
Are you coming around this loop, the upper triangle?
I was trying to do the entire loop. I assumed that meant
Oh,
both of these
outside.
halves at the same time, but maybe it.
If no, you sort of pick which way you want to go.
Oh,
So if you
okay.
want to
That
go
yeah.
this way,
That's
normally if we sort
you're
of
right.
draw it like this, okay, as you've drawn it like this, I guess I would have to come through R3 and then through R1 and then down through this battery. So we could do like that, right?
I guess so.
Okay.
Yeah, I was doing something weird. Dr. Cook says we only need loops 2 and 3 to figure out the resistors. Okay.
Oh yeah,
See you, Thorfinn.
because that one's kind of weird, isn't it? Maybe these are the better place to start because we don't know this voltage over here, which seems like it makes it harder.
Okay. Yeah, I'm
Oh,
not that
and
good
you
with
know what?
circuits.
I've drawn branch currents on here, which are good for if you're doing like nodes. But if we're doing
Mhm.
loops, we don't need the branch currents, do we? We use like mesh currents. Yeah.
Wait, I don't know. I thought the node currents are still helpful, or I don't know the difference. I guess.
Yeah, normally when we're doing loops, I guess you call this like I2, and you call this here I3,
Oh,
and then it's like a loop current instead of a branch current. that's
what you mean, huh?
Yeah, let's do it that way. I don't like any of the stuff I put on here.
Okay. I don't know if I like stuff that I put on either, for the record, but
Well, a
uh,
lot of times in circuits you can do it with nodes or you can do it with meshes, but I think for something like this, the mesh is probably better, like the loops.
okay. Um, so 7 volts is equal to we deal with R2 first because of the way I happen to do it. R2 is 3 ohms. And then plus the same I2 times R1 is 1 ohm. Is that what I'm supposed to do? Because they're in
The 3
series?
ohms the 3 ohms here only sees the top loop, but this 1 ohm over here sees this current and it sees this current here as well.
Mm.
So you'd have to do like the difference between I1 and I2 or something.
Hmm.
You know what? I want to go back to nodes. I think nodes are better.
Yeah.
If I draw it, let's draw it down here.
Yeah, I'll let you. You're the circuit whiz.
I wish.
Hey, Fluffy.
So what do we got? 1 and 3 and 1 and 1. And this is 7. And this, unfortunately, is delta V, which we don't know.
Oh, there we go.
But what we can do is we can ground this. We can say let this be the 0 reference. This is going to be 0 volts here. And so then we have to label a node here. So this up here would now be delta V. Because if this is the ground,
sure.
then this battery raises it. So here I'm V volts above ground, right?
Yeah.
And then here we could just call this, we got to choose one of these other ones and just give it a name. So we could call this one VA maybe. I don't like that. This will be VA. And this will be VA plus 7, right? Because it's 7 above this one. So this battery raises this this is 7 volts above whatever this is what I mean.
Yeah.
So we sort of have 2 unknowns as far as the voltages go, right? We've got all the nodes in terms of 2 unknowns. So okay, and now we got to start doing those branch currents. So we know there's 4 amps this way. And now I got to bring back all these little I's that I erased. So we could call this I1. This is
4 minus
4
that.
minus I1. And call this I2 again, I guess. So this was I2 minus 4, I think.
And that's because the 4 out of the battery means there's 4 into the battery?
Well, so we're thinking about this is, so there's I2 coming this way and 4 going out.
Oh, okay. Yeah.
So basically
Yeah.
the out arrows have to equal the in arrows.
Sure. Okay. Yeah.
And this is I1. This is I2 minus I1 here, isn't it?
Yes. As we said before.
Okay, so all the branches, all the currents in the branches are labeled. Now we just start doing some equations for
the loops.
We don't have to do loops now. We have to do, what do we have to do? Now we just use like Ohm's law through each one of these resistors. So let's see, is there a good place to start? I mean, we could start here and we could say V equals IR through this, across this resistor, right? So what I'm thinking is VA minus 0 equals I2 minus 4. Let's see. Yeah, over 1 kind of thing.
Oh.
So this is like, so it's kind of like Ohm's law. It's like I equals V over R, right? The potential difference divided by the resistor gives you the current flowing through it. And we can set up an equation like this through each of these 4 resistors, and we'll get 4 equations. And I think we have 4, do we have 4 unknowns? I1 and I2 and VA and delta V? I think it gets us where we have to get, but this might not be a Dr. Cook's saying we should have used KVL.
Kirchhoff's voltage law, I guess.
Yeah, which is what you were doing
Leads.
with the two
Okay.
loops, I think.
And Pav, it depends which R's you're combining, I guess. 4/3's probably in there somewhere, though.
My question is, should I persist with this, or is this or is this a bad
I mean,
idea?
what you're saying seems right, too. Hamiltonian dynamics says this works. The other way is easier, but I think we already
I
have
think
this set up. This
so V
works.
equals I. Yeah. So basically, this is 4 equations through those 4 resistors.
Okay. And we want the voltage across and the current through each of them. We should get integer answers, apparently. That's a nice hint.
If we add these two together, we can get rid of I1.
Sure.
And if we triple this one and put these together, we can get rid of I2.
And then we have just delta V and VA, and we can solve those. Okay.
So let me triple this one.
I'll add the other 2 equations. We'll work in parallel, not in series.
Nice.
2VA. I shouldn't say this out loud. God, my handwriting sucks. Okay. And then I added the second and fourth equations and I got this.
Okay.
So I guess we can subtract the 2 equations to get rid of delta V. I guess I should simplify mine. Minus 10. So then those 2 we're subtracting. 2VA negative 12 plus 10 is negative 2. Negative 1?
Okay.
Maybe that's okay, because we randomly called one part 0 voltage. Okay.
Okay, VA equals negative 1, so delta V is 12. 12-volt battery, that seems believable. Wait. No, did I do that wrong? I did that wrong.
1.
It should be 8, I think.
Do these equations not agree with each other? What am I doing wrong? Oh, okay, no. Yeah, it's 8. Yeah, 8. Okay.
Okay, and let's see if we can work out what the currents are then.
Ooh, yeah. I can see like I1 right off the bat. I guess we can even just go back to our equations. If VA is negative 1, then it's negative 1 plus 7 is equal to 4 minus I1. 6 minus 4 is minus I1. Minus 2?
Okay.
So it's just the other direction. Okay. Does that agree with what we said earlier? Well, I guess it doesn't matter.
It's okay. All these things can come out negative. It just means I drew the arrow the wrong way.
Yeah, that's right.
Okay, and what do we still need? I2.
Yeah, and then we know everything.
VA is negative 1. So I2 is 3, I think.
VA is -1 plus 4. Yeah, 3.
Yeah, it works. Okay.
Okay. So the voltage across resistor R1. We go from -1 plus 7 is 6 to delta V, which is 8. So 2? Is that?
Resistor 1, voltage, so IR, I1 times 1,
I'm going across that.
2.
Okay.
Yeah, it should be 2.
And the current through is just I1. Do we care? Ooh. The direction for each current.
You might have. I'm going to draw the picture
Yeah.
again while you label that.
Okay.
Because I like to redraw the picture and see if
-2.
it all makes sense.
So 2 down. Oh, I'm forgetting my units. I don't want to lose points. R2. Goes from delta V to VA. V is 8. VA is -1. So it goes to 9. Yeah. Current through is I2, and I2 is +3. R3, 4, or it goes from 6 to 0, so 6. 4 minus I1, that's 6 down. And R4. From -1 to 0? Then I2 -4. 3, -1, so 1 up. I'm a little worried my signs are off, but...
I got the same
Oh.
currents as you for sure.
Okay.
When it says voltage across, can we get a negative voltage? I mean, I think the voltages across resistors are just positive, aren't they?
Yeah, I end up with a negative, I think, because of the way the current was flowing. I don't know if we should... I mean, oh yeah, the question asking for absolute value delta V, so...
Oh, okay.
I should get rid of that. Oh, thanks for the follow, King Assassin. Okay. Can you... Leo, it's just a definition thing. You can. It's all depending on how you define it. But in this case, it should all be positive. The power P associated with the left battery, is it supplying or absorbing this power?
5 times 8 is 40. And I think it's supplying it. But we can check.
You're saying I2 minus I1 is 5. And it's times V, or it's V squared I, right? Or I squared V? There should be a squared in here. Oh, it's just IV. You're right. Okay.
Yeah.
40. I like that.
So then what we can check just to do a sanity check. So it's 40 there and 28 in the other battery. That's 68 watts being supplied, right? And if we add up all the power being burned in the resistors, it should add up to 68. So let's check it. So I squared R, right? We can do I squared R for each one of these.
Sure.
Let's make it green. So I squared, so 3 9 is 27. 4, 36, and 1, right?
Oh, wow. I was worried that we were going to go
40,
over.
60. There we go. 68 watts.
And we're supplying this, right?
Yeah, well, I just worked out what was being, dissipated in the resistors, but it sort of balances out. So I think we're good.
Yeah, I guess like
40 watts
the second part
supplying.
is
Yeah, we're
okay. Yeah, I guess you can
supplying.
just circle it. Okay, nice. All right. That took
All
us
right.
a
Well,
while,
sorry.
but we got
I
through
think
it.
we did it the hard way because I didn't think of doing loops.
It's okay. Even if I tried to do loops, I would have had to fumble through it. So I think 2 more free responses, and then oh wait, oh my god, problem 3 is a mega free response. But yeah, oh no, never mind. These are both 2 pages of free responses. These next 2 problems. So we have that prompt plus a diagram plus another set of questions.
Well, this is going much
on.
better than I thought it was going to, honestly.
Same.
Yeah. Maybe we really did learn something from Purcell.
Apparently, yeah. Okay, that's problem 2 in all its glory.
Nice.
2 uniform magnetic fields, BL and BR, with constant field strengths that are both positive, point into the page and divide the space into 2 regions. As shown below, particle mass m and charge q greater than 0 is fired with initial velocity v equals vx from in between the 2 regions space as depicted. On the top of the diagram below, give a qualitatively accurate sketch of the particle's trajectory. Okay.
Now we probably need that QVB.
Probably. So it's being fired in the
F
x
equals
direction.
QVB.
So for part A, does BL matter at all?
Well, maybe what'll happen is the thing will start to like loop back.
It comes
and
back in.
Maybe it'll do.
Ooh, that'd be fun.
Yeah, I wonder.
Papa's saying it'll be circular. Maybe. Becoming an electrical engineer? No. Physicist would be fun, not electrical engineer.
Oh, maybe it's going to be. Oh, wait. They're okay, but
they could be equal, but not necessarily. Yeah.
So maybe it'll be like, something like this.
Oh, that'd be so fun if we got like, yeah, if the solution varies with whether they're equal or not, and we actually see that, like something special happens if they equal each other. Okay. What happens in the first instant of time, though? We have V cross B. So point fingers in the direction.
In the Y direction?
Yes. It's going to have an upwards acceleration.
Okay.
Yeah, I think it does come back into BL. Oh, that's so cool. But I don't know if it ever comes back. Oh, wait, but then velocity points in the other direction. Yeah, I think we do get that. Oh, this will be fun to do in Python and actually simulate this. Okay, so I guess that's our qualitatively accurate sketch. Like, qualitatively, not to scale. I think we're doing that.
So what's going to happen with these? So these are semicircles, aren't they? Like semicircular arcs?
Ooh, I wouldn't know if I would go that far yet, but probably.
I got a feeling they are. I think it's like circular motion that you get out of that.
That's a quick maths problem up my first semester teaching for advanced STEM high schoolers. Ooh.
So maybe it's like semicircles that get smaller as they go.
Ooh, yeah, they're not necessarily the same. Like, these amplitudes aren't necessarily the same, or the radii.
Yeah, I'm wondering about that.
Because if BL is bigger, I assume the radius is bigger.
What's the formula again? F
so
equals Q.
We could exaggerate it.
Is it going to lose energy as it travels or no?
There's nothing damping it.
Okay.
I think this goes on forever.
Yeah, so let's say for example that we didn't have left and right, right? Let's say the whole thing was just right, just
Magnetic fields
red,
do
the
no
same color.
work. True. Sorry, go on.
Yeah, then wouldn't it would just go like that, wouldn't it? I mean, if it was just a single magnetic field, it
W-
wouldn't lose any energy, it just go in a circle, I think.
Uh,
So
I guess so. Where does the given coordinate system calculate the net displacement vector delta D from the particle's initial location? Vector delta D. Huh. To its
so
location.
isn't that like this?
Um,
Exits the left side region. Oh, when it first exits the left side
so
region. So that's this.
yeah. Not necessarily POV, they could be the same. But they might not be. Okay.
All right, greater than or equal. We don't know that it's larger.
The current path is not correct.
Wait a second now. I had this backwards. For some reason I thought this was the strong one and this was the weak one, but he's saying the left one is actually strong, maybe stronger.
Yes.
So if it's a stronger field, don't we get a tighter? We get a stronger field. We get a bigger acceleration. I want to say stronger field. You get a tighter circle. So yeah, so it would go like this. I think.
Taikazuki High
Let
Central.
me think.
The path is wrong though. Dr. Cook has told us this path is not good.
Yeah, let's think about the path. I got a feeling the first part is right. Do you agree with this part? I think that part might be right. But what happens
Uh,
when we come over here? We got a velocity this way, and v cross r. It's going in,
this
so it's
tighter
going
circle is
down. No,
true.
you know what? I think it's going to be like this.
Mmm.
Is it going to be like that? It can't wind down like this, can it?
Uh, Wait. Okay. So we know the first part is good, and at this instant we're gonna have V in that direction. Wait, so God damn it. How did I keep forgetting the right hand rule? Okay.
Yeah, the right hand rule.
It does come back down. It doesn't keep
It comes back
going up.
down. Yeah, I think that was my
So
bad. Sorry about that. So
maybe it's like a spiral, or maybe.
but if B is bigger, right, then the force is bigger, and if the force is bigger, it accelerates. It'll be a tighter circle. Isn't that right? Let's think about that.
I'm not
I
drawing
want to
this
say
right. Uh,
maybe it's going to wind up the page like this.
I think it winds down the page.
Does it?
King Assassin, they are both the same direction. The velocity changes though, because like right at this instant here,
Yeah.
it's gonna get an acceleration downwards from the right hand rule as soon as
Yeah,
it crosses
I
over.
agree. Yeah.
So why would it wind up the page?
Well, what I mean is the circle, I think, gets tighter, I think. So it does this.
Ooh,
And then when it gets here,
I
it
thought the
like
circle would
does
get
a bigger.
bigger. But if the acceleration is bigger, tangential acceleration. Yeah, if they were equal, I think we have a circle. I agree with that. Grow my hair faster. Since my hair is getting long, I think I need to cut it again.
Yeah, Dr. Cook said a tighter circle on the left. So I think it goes like this.
Oh, I didn't even see that.
And then when it comes back to here, it should be like it's reset, but it's moved up a little bit. So it should go like that, right? So we
So,
got larger
oh,
circular arc.
okay, sure, because the energy is fixed. So if your acceleration is higher, your radius is smaller. Is that the idea?
Yeah, it's like uniform circular motion. How does that work again? It's like v squared over r. A equals v squared over r. So if you have a larger a and the same v, you got a smaller radius, don't you? Yeah, you got a smaller radius if you got a larger acceleration. So
Yeah.
it's going to be a smaller semicircle here.
Okay, so it does wind its way up. God, that's cool. Something I'm messing it up, but it should be more symmetric than what I'm drawing.
Yeah, that looks right. That looks
Okay.
right. Something like that.
I think that's sick.
Net displacement vector from the particle's initial location to its location when it first exits the left side. So, so now we just need this little. Oh, so it's the difference in the diameters of these circles.
Mm.
So,
Oh, so maybe energy. We know we have an initial kinetic energy.
yeah, good idea. Good idea.
What is this? It has mass m. Okay. This is our like I guess I'll call it K's 0 from the energy that we start with. I mean, we always have this energy, no matter what.
Yeah.
It never shifts into potential energy or anything like that. Maybe ooh. We could think about rotational, like it's a v equals 1 over r d theta dt or something, or is that omega?
Yeah, v equals r times omega.
R times omega. Okay.
What about when you have uniform circular motion? This is v. This is a. So how's it work? The centripetal acceleration is m times v squared over r, isn't it?
V squared over r.
Is it a equals v? I think it's a equals v squared over r, maybe. This is the
Yes, that the
radius.
dimensions check out.
So f equals ma, so mv squared over r. So
Sure.
can we say, yeah, so we can say like QVB. Yeah, I sort of remember how this works. It's because they're always at right angles. The V and the B are going to stay at right angles, aren't they? At every instant they have to, because it's in, because the plane of the magnetic field is going into the page and the velocity is going across the page at all times.
So the
So
cross
they're right
product is
angles.
just yeah.
So it's Q times V times B equals V squared over R. Oh, wait.
mv squared over r.
F equals ma equals m, thank you, v squared over r. And then we're trying to find, what the hell are we trying to find? So what's constant? M's
I guess we want
Q is
r for
constant,
displacement.
constant, B is constant. We want R, don't we?
And yeah, Pava's agreeing with us.
MV over QB. Does that sound right?
Yes. And we'll have a BL and a BR.
So the M, Q, and B are definitely all constant. Is V constant or no? No, it couldn't be, could it? Because R and V are going to change. So when it,
Well, the magnitude of V is the same. Just the direction.
yeah, I'm thinking of just magnitudes in here, yeah.
Yeah, so it's
But
a constant.
I think this is a constant in the red region, and it's a different constant in the green region, right?
Yes.
Because I think, yeah, okay, okay.
Yeah. Yes. Yeah. But we could break it up into pieces. Like we could do the first semicircle as one problem, and then treat it as the initial condition for the next semicircle.
Yeah.
If you know what I mean.
Yeah, I like that. That's a good idea.
Because like we travel to our distance from the first semicircle. And so we already know like
That's right.
So the first distance we travel is 2mv over qbr. That's our, and then we're gonna take that and subtract whatever our next thing is. Speed v is the same everywhere. Even when the field changes though? Oh, because they don't do work. They can't change acceleration. Well, wait, but it is accelerating, just not the... It's just changing the direction, though. I don't know.
Oh, speed is the same everywhere?
Because magnetic fields can't do work. But the rate the direction is changes?
Oh, I'm sorry, guys. I was thinking B was constant. What am I saying? It's not constant.
I mean,
Okay.
it's constant in just the right half. That's why I was trying to break it up, like do a right
Yeah.
half and then a left half.
Oh, okay. So M and Q and V are constant, but the B will change from side to side. Oh, okay. Oh, well then couldn't we say this? We could say B times R is MV over Q, which is constant. So if it's a stronger field, it's a smaller radius of curvature and vice versa. Which is what we said. Yeah, okay.
Yeah, Fizzbuzz, this is the next midterm after that, the one that Zach did.
Hey, Fizzbuzz.
We're hitting this really neat problem with uniform magnetic fields, but split in half. And I definitely want to code this up in Python at some point.
Yeah, so okay, so you said it's 2mv over qbr, and then we would just subtract 2mv over qbl, wouldn't we? Yeah.
Only one of them. Wait, no, you're right. Two of them. And so if BL equals BR, we get 0, and that's to be expected.
Sorry about the handwriting.
Oh, that'd be fun, Fizzbuzz. Fizzbuzz is saying he wants to do on his stream, and then have us heckle him as he struggles to remember things. There's a final, too. This is just like a second midterm. We could do the final, too, at some point. I think this is our answer to part B, though.
Yeah, this is fun, Dr. Cook. This is a good exam. Really
yeah.
Good.
King Assassin, yes.
So what do we need here? The net displacement vector delta D. So we better write this as a vector. So we got to make it times
in the y
hat,
direction?
Right?
Yeah.
Yeah. So we could say delta D equals just this times y hat.
Yeah. I don't know, like, I'll just phone it in and copy paste the thing that you said and stick a y hat on it.
Nice.
Y hat. Okay. Number of triangles. We haven't had that many triangles in this exam, actually. Use displacement time to figure out the net velocity of the particle. Yeah, it'd be cool to, like, completely figure out everything about this situation. It seems really neat.
I think that's the next question.
Oh. Okay, how much time delta t has passed when the particle first re-enters the right side region with BR?
Yeah, so it's the same. Isn't this the same thing we just worked out, like the two semicircles? Like,
hey, Ming. How much time delta t has passed? First re-enters Okay, yeah, first re-enters the right side. Yes, so that is the same like point in time. Combine this. Result from part B. Okay, let's
Oh, well.
read the first
Oh,
part.
okay. Well, Dr. Cook gave us a hint. He told us that the V doesn't change. So now all we need to do is calculate the two half circles, right? Circumference, because we know, yeah, because we know R1 and we know RL and, right? Does that make sense? So the right hand radius is MV over QBR, and the left hand radius is MV over QBL. So we just we add those and multiply by pi to get the total distance traveled, and then use distance as rate times time, right? Let me write it down instead of
Oh yeah, we just need
being
to get
silly.
the circumference, sure. I like that.
So
Let's
right
see.
semicircle.
Yeah, Ming, we're super rusty on this too.
I need pi times this, don't I? Because a semicircle is pi times.
Yeah, pi r.
So total distance traveled.
Yeah, and we're given v. So distance divided by v.
And that
Wait,
equals rate times time.
that's just the radii, or that's like uh. Oh no, or sorry, no, this is fine.
Yeah, I was thinking circumference is
It
2
happens to
pi
look.
r. So
Yeah, yeah. It. This is right. I got
so
mixed up
all
because
we
it
do
looks
to
like the
get
last
the
thing.
so the time, we just throw out the v, don't we?
Yeah, it
Because distance
cancels.
is rate times time. So just
Sure.
throw out the v and we'll have it.
Um. Yeah, Dr. I was confused by that at first, but I think we're on the same page. It's the same point in time, just exiting versus entering. Do these units actually? That's kind of crazy if they check out. I guess the magnetic field is going to be where the cancellations come from. Whatever a Tesla is. Combine this with the
So
result. Oh, sorry, what?
we're saying that's delta t.
Yes.
So the average velocity. Oh, a lot of stuff. Oh, wait. I wanted these things in parentheses to cancel, but one of them's a sum and one of them's a difference, so they won't cancel.
Oh, that's annoying. It
Yeah.
should clean up a little bit, I guess. Maybe. Maybe not. It'll be like BRBL.
Sorry, Don. I started writing too big, didn't I?
Oh, no, that's fine. Um, is the velocity vector... How does the... So it should be... Wait, the average velocity vector... I'm a little worried about the direction. We're going to get the velocity vectors pointing upwards in the y direction from this. Is that good?
Yeah, it should be because it started here and ended here. So the average velocity should
Okay.
be in the upwards y direction.
Yeah, and that's not what the actual velocity is, which is what was making me worried, but I guess we're okay. How are we calling this? VAV? Okay. I am crowding my work with your work.
At least the M's and the Q's are going to cancel.
Sure. That pi is weirding me out, but it can be there. So we're getting 2v over pi. And then if I multiply
Should
all
we
this...
multiply everything by BL, BR?
Yeah.
Okay.
I think it looks like that.
Y hat.
Y hat. Okay.
We didn't put boxes around our answers.
Oh, yeah, that's fair. Minus 1 point for missing the vector direction. True. Yep. Femvox caught me. Richard Hamming once said, if a design of an aircraft hinges on a function that is Lebesgue integrable but not Riemann integrable, I'd not step on that plane. Is that... what kind of function does an aircraft rely on that's like that? Or wait, oh no, that's... Sorry, that's not, like, literal. I see. He doesn't believe in, like, Lebesgue integrable only functions. That's funny. Sorry, I'm looking at the discussion in YouTube chat, Fembox.
Yeah,
about, like...
no, I saw.
Okay, yeah.
I remember hearing that quote recently. I don't know where.
Yeah. King Assassin, it's an extension to Riemann integration that works on more types of functions. But the point of that quote is that Richard Hamming doesn't quite trust it. I guess. For each special case below, argue a sketch helps what VAB should be in that special case, then verify from your result from C reduces correctly in that special case. Well, for part 1, I should be 0. Right?
Yeah. Yeah, because if they're equal, it's just making a circle. One single circle.
0.
Oh, and yeah,
circle.
we got what we got. If you let BL equal BR, we do get 0.
Yeah.
Nice. Okay.
Yeah, exactly. Central. We're doing physics, which is hard. Goes to 0. At an actual purpose, what face? Yeah. Ooh, if BL is much greater than BR. It's going nearly, like, tangentially in the Y direction, right? Just in a straight line?
Let's see. If BL is much bigger.
So, and this fraction is approximately 1.
So we get 2v over
At its lesser speed, interestingly. Huh. Does that make... That doesn't feel right.
Yeah, because if BL is much bigger, then the second semicircle is basically tiny. You know, it's just sort of... Oh yeah, so the graph will look more like... I think the graph you'll get will look more like this. You know, it'll be just like this. Right?
Yeah, that's probably better.
So it would go like this and bounce, and you know, you get a tiny little circle here you wouldn't even notice on the left.
Yeah. Okay. What should VAV be? I guess it would... VAV would be about 2v over pi y hat.
Now,
Still,
does that make sense?
I like your drawing for sure.
2v over pi. So how far did it travel? So v was...
Yeah,
Yeah, where's this factor of 2 over pi coming up?
I don't like it, to be honest.
Well, wait a
But
second.
it is
Okay.
average.
Think about this circle, right? That circumference. Yeah, what's the... Okay.
And for every distance 2 upward, it moves pi greater than 2 distance. So the average velocity vector has magnitude reduced by factor pi over 2. So I think he's saying
So it's
we're right.
v. It's v divided by pi over 2.
Yeah. I don't quite know how to think about average velocity, I guess, because I guess we're right, but it kind of bothers me because of the energy. But it's not the same velocity as we use for energy. I think we're right.
Yeah.
Just...
Yeah, I think we're right.
yeah.
If the... So we don't... So let's just say this thing had radius 1, right? This circle here.
Mhm.
If it had radius 1, yeah, then this distance would be 2. And if it has radius 1, the circumference is 2 pi, so this arc length would be pi, right? Yeah, there we go. There we go. So it's a ratio of 2 to pi. It's... So if we're going v units per second along this arc, it's taking us pi to 2 times as long as if we'd just gone straight up the middle, right, at v.
Oh.
It feels right.
Okay. And Dr. is saying we are right, so... pi over 2 is the inefficiency, in quotes. Or the reciprocal, yeah.
2 over pi. Okay.
All right, final problem. It's another one with a bunch of, like, pieces to it, though. Yeah, King Assassin, I really like that problem.
Yeah, it was cool.
I don't know if I would say I'd have fun with it on an exam, but I did have fun with it in this relaxed environment. Okay, an L by L square loop of wire lies in the XY plane as shown below. The loop is placed in the presence of a non-uniform magnetic field of the form that, where B not greater than 0 has dimensions of magnetic field. Oh, and that's okay. I was wondering about the divided by L, but that cancels with the Y and the Z. Sketch a magnetic field on top of the XY plane given below. Do this by drawing the local magnetic field vector at each of the 25 grid line intersections. Oh god.
Yeah. Okay.
Ensure the relative magnitudes and directions of your vectors are qualitatively correct. Oh god. If B is 0 at a particular grid line intersection, mark that point with 0. Spend at least 20 hours in each exam you make.
We're in the
Wow.
XY plane. Okay, that's good. And so if y equals 0, we got 0, don't we? So I think all these 5 would be 0.
Oh, we don't have to do any right-hand rules. Oh, thank God. Okay. Yeah, we just look at the vector and plug things in.
Yeah.
So, wait, yeah, Z is always 0. That's what you just said, right?
Yeah, because we're in the XY plane.
Okay, good. That makes it easier to draw. Then it only
So I
depends
think
on
these...
Y. So all the X's... Yeah, okay. So, like, everything in a row is always the same.
Oh, yeah. Yeah, for a
Um,
constant y, they're all the same. Okay. So 4 comma 1.
4, 1. Yeah. Uh, I guess. Okay, so those are all zeros. That's what you drew on that home row, right?
Yeah.
Okay. Then say like one row up, yeah, 4 comma 1. So we don't just something that's steeper than it is tall, I guess. Well, that's not how I. Whatever. It's less than like a. Maybe I should draw them even flatter, like that.
And if we double it, they'll be the same direction but twice as long because it'll be up
Uh
8 and over 2 or
oh,
over 8
sure.
and up
Maybe
2.
I should draw them shorter then, so we have room to grow. And I think negative wise, we're going to flip the direction, but otherwise the same.
Yeah, exactly. Okay.
Also, okay, I was a little confused at first. 'Cause I thought the loop was producing this field, and I was wondering how that's possible. But no, this loop is placed in a field like this. Okay. Students draw more on the exam itself, just kind of break things up from pounding algebra. I really like that, Dr. Cook.
Yeah, it makes it more fun.
So I remember on one of the exams he sent me a long time ago. You had a really fun one with like a circular electric field, and you had to find paths with like positive work, no work, and negative work or something. I really like that one too.
Oh, I remember that. Yeah, I remember that.
Yeah. Is that part A done? Yeah, I think so.
Yeah. He used Ampere's law to determine how much of the current sourcing must be enclosed by the wire loop.
Wait, how much?
How much of the current sourcing B must be enclosed by the wire loop?
What?
Does this enclosed current flow into the page or out of it? Okay. So
Closed by the wire.
what's Ampere's law again? I know I've asked you that like 3
Oh.
times.
Yeah, that's b dot ds mu not I.
Do we integrate around
That's our
the
C. Yeah.
a wire?
Okay. Yeah, the word sourcing I was getting stuck on, but it is just like, yeah, this makes sense. He got some pages of algebra and his little calculus ODs. Oh, that sucks, King Assassin. I had some fun drawing problems in my PD's class that were really good.
So do we just do 4 little
Um,
line integrals like this?
I
4 line segments?
guess. Yeah, I'm looking for a hand wave right now. The dot product, I don't think. Mm, I think the sides might cancel. That's possible. Because in one, the S vector points up, the other one, the S vector points down.
Oh yeah, the left and right sides. I like it. Just by symmetry, right?
Hamiltonian dynamics agrees. Yeah. So
And the
maybe we need to worry
bottom's
about the
0
top.
because the field's 0 everywhere on the bottom.
Yeah, and the top one is constant. Like it's gonna have the. We can just calculate at one point and multiply by the length.
Okay.
Okay. Um. Winklebot, you had some pretty crazy series though. We're both pretty good at calc too, so I bet we could get through it. But I remember you had some weird series. Okay, so we can just take it at the B field at any point. On that thing. So the Y is L. 4L, L, 0. And we need to dot it with a vector pointing upwards.
Why upwards? What do you mean upwards?
It's like if the entire enclosed path is that square, we need a. Oh wait, no, I'm sorry. Pointing to the left or right. I was thinking of like an area vector. This is a line one. It points along the path.
Yeah.
Which way are? Oh, we're gonna be off by a sign. Does the phrasing imply a certain way? I guess as long as we're consistent, we should get the right answer.
Yeah, as long as we're consistent, right? It should be all right. I mean, I drew the loop going this way, but
okay, we'll go your way. So we need to dot with a vector pointing to the left. So a unit vector. So just 1, 0, 0.
Is it minus 1, 0, 0?
Yes, thank you.
You could cancel those L's if you want.
I sure could. Thank you. That's not. One day I'll learn what my hotkeys are. And then times the length, which is L. That's. Oh yeah. Thank you for catching that. That's a 1, right? Yep. Okay. It's gonna get thrown away in a second anyway. Yeah.
Where does L come from?
That's the length of the integral. The length of the path.
So it is. Gotcha. Is it or is it 3? Oh, it is L. Yep. It's L.
Just for the upper part, at least, yeah. How does that feel?
Okay. So that equals mu naught times I.
We need L for dimensional consistency. Oh yeah, that's true, Ming. How much of the current sourcing must be enclosed by the wire loop? How do we figure this?
How much of the current sourcing B, X, Y, Z? How much of the current sourcing the magnetic field must be enclosed by the wire loop?
Oh, wait, so we went counterclockwise and got a negative result. So the actual magnetic field is going... Wait, oh no, we know the actual magnetic field. Never mind.
Should we say this?
I
enclosed?
We can say that.
So this
we do
I
need
enclosed,
to say that, yes.
That I enclosed is like current flowing through the inside of that. So there's some kind of wires inside here that we haven't been shown. Is that what's going on?
Yeah, it must be a crazy enough wire to make a field like this, but a wire, yeah.
Well, if we just solve for I, we just divide by mu naught, right?
Yeah. And that would be our answer for the first part of the problem. We have to deal with the cursed right hand rule again, though. I think for the in or out. I think it flows into the page. Because I'm doing the right hand rule, and if I close my hand to the right, my thumb points into the page.
Yeah, because he told us that B0 was positive. So
Yeah.
Okay, I agree. So it goes into the page.
Okay. Part C. Suppose a current I naught now runs in the wire loop counterclockwise. Upward on the right edge. Sure. Calculate the net magnetic force vectors F bottom, F top, F left, F right on each of the edges of the wire.
Hmm.
Well,
I
so
bet you the bottom will be 0.
doesn't the wire doesn't make a magnetic field inside itself though, doesn't it? Like if it's a thin wire, right on the wire, there's no field, is there? From that wire.
Right. Right.
The edges. Oh, I guess the other parts of the wire
Isn't
are
this
affecting it though. That's the point.
isn't this F equals Bill?
Probably.
Except we might have to integrate because it's not a constant B.
Ooh, the vertical sides are not. Yeah, Ludwig, we're almost through this. You can try me after we're done here. Oh, that sucks. Or I'm glad he let you fix it, King Assassin. That's annoying. Okay, so I do think we need to worry. Oh man, you're right. Okay, because this seems annoying. Hopefully, that's a way we can simplify this. But like this bottom wire, we do need to affect it, or we do need to account for the other 3 wires making a field on it. Dr. Cook says it is
Really?
a Bill problem. I think we do, don't we?
Oh, Dr. Cook says I naught is weak enough to neglect the field it creates.
Oh. Okay. Then what's the problem?
Bill. So
But if we get to neglect I not, what are we doing?
we've still got B. We've still got all these magnetic fields in the given magnetic field, right? And now we have a
Okay.
given current and we have given lengths.
Oh,
So
okay.
so I think it's just like 4 little individual problems.
Okay. Yeah, because Bill it has the current from the wire that, or like from this wire in the loop, not from the current we just found. I hope.
Exactly.
I think. Yeah.
Exactly.
Okay.
Yeah. Yeah. Well, yeah, because the current we just found, by the way, I don't think it was that wasn't a current in the wire, right? That wasn't a current flowing in the wire. That was a current somehow in space being like going through the region enclosed by the wire, right? Isn't
Yes.
that how that works? Okay,
There's
yeah.
some wire that
Yeah.
we can't see that we were enclosing.
Yeah.
Bye, Ming. Thank you for hanging out. Probably 7 inches shorter, Leo. Okay. So the top and bottom are probably easier than the sides, right? Because we can just use Bill directly for the top and bottom.
The thing about Bill is, I remembered it because it made a guy's name and it was funny, but I don't remember but I don't remember how it actually came about, because I know it wasn't just Bill. It was like I cross L sine theta or something. I forget where it actually comes from.
I
So
think
we
it's like
might
the
need
simple
to.
case of Bio Sava.
Oh, is it? Yeah.
Um, it's probably in the. I remember seeing Bill and laughing to myself, like, "Oh, hey, it's Bill." It's a solenoid. When I first saw this problem, I did think it would be like an induction lenses law type of problem. I'm a little surprised there wasn't one, but maybe Dr. Cook's class couldn't cover that.
IL cross B.
The Lorentz force law. Oh. Is it in the next chapter? It's kind of annoying me that I can't find it now. Even though we're being told what the answer is. Oh, that's Bill. I found
You
it.
found it?
Yeah, in the Purcell book. If a wire carrying current I2 lies perpendicular to the magnetic field B1, the magnitude of the force on a length L of the wire... I'll screenshot this and bring it in, actually, so you don't have to listen to me. It's a lot of words.
So that comes from Lorentz force law, huh?
Yes. Oh, I probably just wouldn't show it on stream then, if there's a worry about privacy, Cook, but it would be nice to know if we're right or wrong. Wire carrying current I2.
Perpendicular to a field. So then couldn't we
Maybe we
just
need to go back to the Lorentz force.
break the field into components? So if it's
Oh,
parallel, then there's no force? Is that the case?
yeah, that makes sense.
Yeah, so for example, the top wire, we could just break that field up into, I mean, we only care about the Y component of the field, right? For the top wire. Oh, and for the left and right wires, we only care about the X component.
Oh, and that's... Well, yeah, that's constant. Is it? No. Y, X depends
No.
on Y, confusingly.
Yeah.
Okay. QV cross B for a wire becomes IL cross B. Oh. Sure.
QV is IL.
L points with the wire, B points with the field, I would think. And that's I not in our problem. So if we're keeping our counterclockwise convention, which we should do because that's how the current runs. Yeah, let's keep focusing on the top wire. So L, I guess, is -100. B is B not 411 or 410. Wires B wiring.
Do we need an L here?
Do we? No,
No.
this is L. Oh wait, that's not L. That's L. Is that L? I think that's L.
I think so. Yeah. Okay.
I hope that's right. I guess we can work this out. I don't know where scalars can come outside of cross products. I assume they can, but you just be
Yeah.
safe. Okay.
Zero. Oh, it's just a K, right?
Did you just get a determinant mentally? I guess most of these are. Yeah, there's a lot of zeros in here.
So it's B. So it's minus B naught I naught L. K. Bilk.
Bilk.
Bilk means to rip somebody
Yeah.
off.
Does
Let's
that
see,
make sense
negative
in the
K,
K direction?
the negative K hat direction.
Yeah.
So
It goes into the page.
so that means it's going down into the page.
I think that agrees. Maybe? V cross B. V cross... Yeah. I like that. Comparing it to like the general Lorentz force, what we should get.
Okay.
And yeah, I think negative K is good.
So that's F top. So we're saying that's F top, right?
Yes. I think we can safely say F bottom is 0.
Yeah. Oh, don't peek.
Oh, I saw my Discord light up. I didn't see what it was though.
It's probably answers.
Yeah. I assume left is negative of right. So we need to work out 1.
Yeah.
Yeah.
Yeah, that's right.
Oh, it's censored? Okay, cool. Now that is an integral, I think. But probably a simple one. Because we only care about the perpendicular parts.
So do we have to do yeah.
We know...
So which one do you want to do? Do you want to go up the right-hand side or down the left-hand side?
I guess... It's not a big difference. I guess let's go up the right-hand side.
Okay. So what does that mean? So in this case, we can't just let L be a constant, right? We have to let L be a in terms of dy or something.
Yeah.
Yeah.
4y, y0. Dotted. I don't know what to dot it with yet. This is the field. We need to dot it with the vector for the line. Which is 0. A unit vector for the line, in this case, I think.
Oh, wait. If we dot it, we get a scalar. Don't we need to...
I think we want a scalar. Or wait, no, we
Do we?
don't. Sorry. Do we want the cross?
I
So,
think the L will just be like a DL, won't it? And we do a DL crossed with B. But how do we write the DL? Just 0 dy 0 maybe?
yeah, that sounds good. Cross vector DL, Dr. Cook says. Okay. So I think it's just what I had written with the cross product. Because this dy is like a scalar multiple of that vector, I guess. Oops.
Yeah. Okay, I see. I got you.
Okay.
So
We can cross that up.
yeah, cross it up. Okay. Oops.
Y 0 0 1 0. Let's see if I can do it as quickly as you did that cross product. The I, there's no I component. J, we have a sign flip. Oh, there's no J. And then K is 4Y.
And then just dy, right? Okay.
Is this like an element-wise integral? How does this work?
Yeah, so we get 4y k hat dy, and we integrate it.
Okay. We can just do that, I guess. B naught over L.
Aren't we missing an L though again? Maybe we needed an L here.
I think that's ooh. I feel like that should be a unit vector. I think the L is taken care of with the bounds.
Okay. Crossing like AI.
I don't know what that means. 2 B naught L K hat.
Is that a real person, Alan Iverson?
The initials are AI. I'm not sure.
Yeah.
Wait, so we get positive K direction now instead of negative K.
We don't have an I0. What happened to our I0? Oh, we just need an I0 tagged
Uh
onto this, I think.
oh, sure. I forgot. I should
Yeah.
have had it from the very beginning. Basketball player famous for his crossover. Oh, okay. Actually, I'm still not sure what the crossover is, but I don't know. That's F right. I guess F left is a negative. Um,
Oh.
I don't know how to feel about this.
So, well, it's like post-physics bliss. That's what I feel.
I guess should we look through the answers?
Yeah, I mean, we're done, right?
Okay.
Oh, wait. What did this question say? Suppose a current now is net magnetic force vectors on each of the edges. Yeah, that's what we did.
Okay.
I think we're finished.
Time to have the moment of truth. Oh, wait, Cook, something got messed up with what you sent. I only have the first page, and it's like an image. Should be an image.
Just the first page, right?
I only see the first page. Like the first, only one image. Scroll through like a PDF? No. Try that. Okay. And I'll open it off stream, at least at first, to make sure I'm not showing anything. Oh, I see the word
All right.
Half-Life written for that one problem. The exponential decay. I'm scrolling through it quickly to make sure, like, it is, or, like, everything is censored. I think it is.
I think we got
Okay.
all the multiple choice right.
Oh, really?
Well, to be fair, we had a little bit of help now
That's
and again.
true. A little bit of help from our friends.
Yeah.
Our number one was C. Is that what we said? Yeah.
I think so.
Number 2 is A. Noise. 3 is C. Good. 4 is D.
Three is D. 3 is D. Did we get D?
Yes. Oh, did I say that wrong? Yeah. 3 is D. 4 is also D. Yep. 5. B. Noise.
That's the one
6.
that we had so much trouble with.
Yeah, maybe like our least confident one. 6 was E, 32 watts. Noise.
Yep.
7B, that's the Half-Life one. 8E. Heck yeah. Alright, so we nailed the multiple choice. Free response, part A, 4A to the left, good. This table, 2293. Ooh, I don't know about this. Oh wait, 2293, 6622. Wait. Those are twos.
Dr. Cook's 1 looks a bit like a 2.
Yeah.
I think that's a 1.
Okay. Yeah. So, yeah, we did a sanity check. That has to be 1. Okay. And then part C, 40 watts supplying. Good. Did that right? For your response 2, displacement vector pointing up. Hook strong is a lot neater. Part B, 2mv over q. 1 over br minus 1 over bl. Good. Y hat.
Nice.
Part C, m pi over q with a plus. Good.
Is that what we got?
Wait, part C, m pi over q. Yeah.
Okay.
And then, wait, what was our delta t? Yeah, okay, that was it.
Oh man, we kind of destroyed this. I mean, come on.
I
I feel good. We kind of ruled this.
Yeah, and we did have help. I think it wasn't that much help. We kind of cooked like Dr. Cook.
We even had those diagrams with the little circle halves of circles there.
Yeah.
Honestly, this last one I felt less confident.
It got a little sketchy at parts.
Yeah.
I think we got our vectors right. I'm trying to decrypt what this is saying. Part B. For a counterclockwise loop with n hat going out of the page?
Yeah.
Didn't we say it was going in? Or maybe we're
Well, he
just
said
defining
in the
things.
box, he said it's into the page. So I
Oh,
think we're,
okay. 4b naught L over mu naught?
you know,
Ooh, do we make a sign mistake, though?
we never stripped off the negative sign, and I was
Oh,
wondering about that. He's
well,
got
that's
absolute
fine.
values around the current there.
So yeah, we have like an invisible times positive z hat, I think. I think we agree.
Yeah.
Okay, part C, F bottom is 0. That was the easy one. For F top, I naught L B naught minus C. Is that, yeah, that's what
I
we
used
have.
K instead of Z. Is that all right? I just
Yeah,
used K.
that's fine. If we get marked down for that, then in my course evaluation at the end of the semester, I'm taking off points.
uh,
Trying to be careful. Yeah, I was kind of confused about about what it means to get a minus sign. So it is weird. And then so right and left, they are just opposite signs. 2 I naught L B naught. Yeah, okay. Wow. We
well
did really
done.
well.
That was great.
All in a day's
Had a
work.
great time.
Yeah.
Dr. Cook, great exam again. I really enjoyed it.
Yeah, this was really good. I guess we should do the finals sometime too,
we'll have to look
maybe.
at that final
Yeah.
sometime.
Maybe we can give it like 2 weeks or something and then come back to it.
Yeah, I want to go through some more of the MIT stuff in the meantime.
Yeah. All right.
I think I was a little lucky because there was so many circuits questions, and I felt like I had a little bit extra strength on those ones.
Yeah, I was a bit worried we were gonna get some induction or like
We dropped a minus
electromagnetic
sign,
waves. We did?
I don't know. Dr. Cook's saying we might have dropped a minus sign at the end. Probably did.
I did bill in the wrong order in the integral. We did bill dirty. uh Wait, I'm saying F right.
Yeah, we got the signs backwards, didn't we, on left and right?
What went wrong? We did flip the signs.
Yeah, but where?
I don't know where. In the cross product? Oh, what a simple mistake to make.
Have we got the cross product set up backwards? You did BIL in the wrong order. Did we do BLI?
L cross B? Oh, I did B cross L!
Oh.
What a rookie mistake.
Well, you know, it wouldn't be right if we didn't get at least one negative sign in the wrong place. I've never been able to get through a physics exam without getting at least one negative sign in the wrong place.
That's fair.
I think it's sort of mandatory.
Yeah, we just had to throw that in for old time's sake. Okay, well, I guess we got like a 99% then. We'll have to live with that. Could have seen
that was great. That was really good.
Yeah, I did that for F top even too. I just didn't think about it for the sides. Good theoretical physicists make an even number of sign errors. If you do L cross B, you should see it's into the page. Okay.
All right.
All right.
And thank you, chat, for keeping us in line too. That was great.
Thanks for coming on the stream. $10.
Yeah, Don. Thanks again. We'll do it again sometime.
Yeah. All right, see ya.
All right, see ya.
Man, I feel like such a nerd when I say this, but that was actually really fun. Let me get some music going, and we'll just turn this into a normal math stream. I still have some energy here. Music am I gonna play? I guess we'll just go a little reliable. Wait, that's not the right playlist. That's the right playlist. We'll have a little celebration and play the song. Yeah, I especially after doing this, I want to do the final even more now. I think we export image, yeah, and then copy to clipboard. Just for posterity, I'll put this into, I guess, just my Discord. You never know. In like 6 months, someone might ask me an E&M question, and I'm going to be like, oh, this is like that one question that Dr. Cook had. Okay, I should change my stream title and all that. Answering your math questions. What am I going to do if there are no questions? Bloodwood, are you still here? Do you have your combinatorics questions still? The music's a touch hot, isn't it? You have it? Oh yeah, let it rip, please. Change my YouTube title. How do I change my YouTube title? There it is. What do I make my YouTube title though? Math, office hours, and studying. Boy, I need to figure out a better YouTube title. Okay, I have a copy of the Excel address saved, so I can close out of that. Honestly, if there is downtime, I might just pull some more E&M problems. I can even try to code up that uniform magnetic field problem too. But let's at least read Ludwig's question here. How many possible unique sequences, exact placements of chess pieces are there in the first 3 moves of a chess game if the 3 pieces moved are a pawn, a knight, and a queen? It really is Hamiltonian dynamics. Before I did the E&M study group with femvox, I used to tell people that I don't like physics, I don't know physics, I can't help you with physics, but studying E&M with the advantage of knowing multivariable calculus is just such a game changer. You did, Cook. So I assume this is any pawn and any knight. This feels doable. Let's get an image of a chessboard. That'll help. How do you get an image of a chessboard? Analysis board on Lee Chess. So we can even play in this wow, thank you, Stockfish. We can even play in this thing if we wanted. How do I get rid of the arrows? What? Arrows, can you please fuck off? I don't know how to get rid of the arrows. Here we go. I just want a screenshot of this. Any pawn won't work. There are only 3 pawn moves that work. Any pawn. I mean, no. We. If I move, say, the H pawn, I mean, I can make all 3 of my first moves the H pawn. Oh wait, no. I'm sorry. You are required. I see what you mean. You're required to move all 3 of these. Yeah. Okay, I see what you mean now, Steven. So we can only move 1 pawn. And so I agree with you, Steven. There are only 3 pawn moves that work. Except there's actually... Well, no. Okay, yeah. Only 3 pawn moves that work. We do have a... This is kind of annoying. This pawn move blocks a knight move. C3 and F3. And I assume we're only counting one side's move. I'm ignoring black here. Do we... Actually, I don't know. The phrasing of this is not good to me. Because in the chess world, move 1 is a white move and a black move. Yeah, and so Steven, I think, has the better phrasing of plies, which is like half a move. Because I don't imagine the question wants us to consider, like, white playing d4, black playing e4, and let's say I just bring my knight out, and then, like, if black can take our pawn, that throws another wrench into the gears that I hope they don't want us to have to figure out. One player... Oh, so... One player... White makes 2 moves, black makes 1 move. That makes this probably even simpler. Because there's very few valid... sequences then, I think. That's a good thing. So how do we think about... I assume white has to do the pawn and the queen, and black does a knight. Part B, solve chess. Because, like, if white does a knight move, black does a pawn move, because black can't do a queen move, then white can't do a queen move. So I think it has to be white does a pawn move, 1 space or 2 spaces forward. Black does a knight move, and then white does a queen move. Yeah, Lucas, it's a chess problem. You have an answer, no idea if it's right? Phoenix is calling 8 times 3 times 6 times 4. Let's see. Well, I think white only has 6 possible pawn moves, right? On move 1? Any of these 6 squares. So, my first number that I'm throwing out is a 6. Black has 4 possible knight moves, so that's a 4. Yeah, I really don't know where you're getting your... Unless you're doing this in a different order, Femvox. And then we need to deal with queen moves, which I think are case-based. They are. So we're gonna need to break this up. Let's deal just with the D pawn first. If we play D3, black still has 4 knight moves. White has 1 queen move. Now let's do 1d4. 836 correspond to the 3 different pawns. That feels like way too high, though, doesn't it? 40 possible. Oh, nice. Yeah, Lucas, the phrasing of this is weird. They're talking about like plies. So white moves once, black moves once, white moves once. Is what they're actually asking. So the question is a little bit weird in that case. If we have 1d4, we only have 2 possible queen moves. So that's what we get there. If we play, maybe let's think about c3, PO. I should just remove the leading ones. I think we're going to consider all these individually. Uh, 1c3. Yeah, Lucas, that's what we're looking at. So if we play 1c3, white has 3 options for the queen. If we play 1c4, the most explosive move, same thing, right? And I think d3 and d4 will be the same thing, but +1. 1, 2, 3, 4. I think whatever this is our answer. Uh, 4, 8, 24, 32. 40 plus 28 is 68. Hey, another 68, just like the 68 watts. 3 moves total, like 3 half moves, Lucas. It's like white moves 1, black moves 1, white moves 1, and then how many possible things are there? You got a different answer. You got 215. I feel pretty good about my answer. I don't know. You ever gonna buy a long way? Okay. Ludwig, let me know if this makes sense. I feel pretty good that 68 is the correct answer. I think we could have made this problem a lot harder. I'm glad it didn't turn out to be that hard, because it would get annoying to count that much. Oh, you don't know the answer? Okay. I feel good about 68. No, Winklebot. What do you come up with? Do we do some Purcell problems right now? You think it's more? Algebraista. Oh, I remember that now. Yeah, you did share that. It's a good one though. I think maybe as when we were watching the videos, I feel like I wasn't able to respond properly then. I don't remember. Two more names or two more problems or what? Names? Yeah, what are they? They are hard, Femvox. I agree with that. Flowers for algebra. That's a good one. We could try to code up Dr. Cook's problem, actually. That could be fun. A depressed... Yeah. That's a really funny name in math to me. Six possible variations with pawns on move 3. Right? Wait. I'm not sure what you mean. There are 6 possible, like, ways to have the pawns. Like, you can have them on any of these squares. Abelian groupie. Yeah, so those are my 6 cases on the right side here. Yeah, and the first move does need to be a pawn move. If you do e3, you have 4 queen moves. No, so if you do e3, you only have 4 queen moves. So 4 times 12 is overkill. Oh wait, I'm sorry, that's what you're saying. It's not. Wait. I don't know where you're getting 12 from. Are multiplying by 2 again because of symmetry? Um But yeah, so I wouldn't take the total, like... The problem is that each pawn move, depending on the file, you have different numbers of queen moves. So you have to split them up. You can't just group them all in one thing. British countries doing kinds of collective effort will be mildly amusing names for Excalibur based on math puns. Because, like, if you play c3, you only have 3 queen moves. C3 PPO? Just wait until you see R2 D2. Hey, Energy. I remember you said you might have a question the other day, and I was able to help you. If you still have that question, let me know. It's a good time. Oh yeah, let me know. Winklebot. Uh, oh, if Google AI says so, it must be true. I don't know. Well, wait to hear Energy's question. I could go back to linear algebra type of stuff if we want to not have physics in our life for a bit. I don't know what I want to do. Okay, Energy's asking about the Picard-Lindelof theorem. Existence of unique differential equations for open subsets number line. It's relevant for machine learning. Hmm. Ooh, really? That'd be fun, Dr. Cook. It's unapplied physics. Yeah, I would love some linear algebra exams. Probably wouldn't do them today, but like, I would absolutely do them. Um, Machine learn. I have a hard time imagining this would apply to machine learning. I'm not aware of differential equations in general being related to machine learning and energy. Uh, it could be for all I know. But this is at least a theorem that I've encountered, which is a nice change of pace. uh, like I am familiar with this theorem. You thought some machine learning is continuous. I wonder if continuous in machine learning means something else. Taylor series exam? I'd have to erase your work. uh, if I guess I could take screenshots of just the problems. If you, yeah, Winklebot, I think I can work with that. Let me try Googling differential equations. Well, not that. From basics to ML applications. This is an AI generated image, if I've ever seen one. Let's see, did it get, it got the heat equation right, I think. Oh, it has a non-homogeneous part. Huh. Gradient descent. That's fair. I don't know if I would call that a differential. I mean, I guess that's a differential equation. Hey, Kalman filter. Um, No worries, Winklebot. That one's awful. Don does exams. I mean, I think it's good material. Like it, or I guess like it's good content. If we don't have a question from chat. Okay, so energy. I do know some basic machine learning stuff. Actually, I don't know everything about machine learning, but I'd say that I've dabbled. I have some repositories on my GitHub, where I do like supervised learning, unsupervised learning, and semi-supervised learning. I never encountered differential equation in that. A lot of this feels like a reach, at least what this particular website is saying. Neural controlled differential equations. Yeah, it depends. So like AI and machine learning aren't quite the same thing. I think AI is a very expansive term. Machine learning is basically fancy curve fitting. Like the most basic form of machine learning a lot of people have done actually. If your data on a scatter plot looks like this and you do linear regression to draw a line through it, that's kind of your most basic form of machine learning, you could call it. Machine learning gets fancier when you start wanting to fit things other than lines. And when you want to start calculating your error in different ways. And I think AI is kind of like, I think of it as kind of like everything about like computer intelligence, I guess. Some derivations of the calculations ML do involve basic DEs. Steven, that's the sense that I'm getting. Like, I think there's something like what I have on the screen right now where you do truly use a differential equation to do machine learning and in some way. I think these are fairly niche though. I think. Again, I've only dabbled in machine learning, so I can't say I know all about what's common and what's not, but I think the best I can tell you, Energy, is that I'm unaware of an application of the Picard-Lindelof theorem in machine learning. I doubt there is an important application of it today. Maybe we'll come up with something in the future where it does, but I don't think of differential equations as a very big part of machine learning. And Picard-Lindelof is pretty firmly about differential equations, as I understand it. Yeah, Steven, like gradient descent is something more like Euler's method, like it's more of a numerical thing, I think. Like multivariable Euler's method. Well, it's not quite like Euler's method isn't the perfect like metaphor where you're doing it numerically. So yeah, I guess that's my answer for you, energy. The more I look at these E&M problems, the less I want to do them. Because I'm remembering how tough these problems were. They don't have much application. I suppose I should focus more on linear algebra, so don't dismiss the relevance outright, given that ML is expanding. Yeah, and so that's why I'm like kind of hedging my bets by saying the word like today and that I'm aware of. You're right. It is an expanding field. And $10, yeah, sure. I would imagine that it would be kind of the theory part of machine learning. Because normally if you have a differential equation, you just kind of throw some numerical methods at it and not worry too much about the existence, I would think. Well, yeah. That's right, Cook. You said you use Griffiths for first, like, for like the first encounter with E&M, I want to say. Grassmanians and Plucker coordinates. No, I've not heard of those. For dimensionality reduction, I think of principal component analysis. This differentiable manifold stuff is not in my wheelhouse, or projective space stuff. Yeah, I wouldn't know. And here's Plucker. I bet it's pronounced like Plucker or something. Could be cool. I wouldn't know though. Plucker? The Flucker? You love them, Tessin. That's cool. It'll take me a lot of studying to learn what these are. Did I miss a thing? No, I don't think I did. So an interview about how these principal component analysis try to distinguish between dinosaur species. That's really cool. Hamiltonian dynamics. I could imagine that being useful in like the DNA data. Levels of intro calc-based E&M. One assumes no background other than calculus. The other goes a bit faster. Usually take my students who take E&M in high school before. So for the first type, usually uses something like OpenStax. Oh, okay. That's right. The example literally said freaking OpenStax. Oh, okay. That makes sense, Dr. Cook. In Ghive, when I checked in the hospital lab for routine blood tests, they gave me a code name for privacy, I guess. The check-in person handed me a few documents, then said, "Give this to the tech. They will be calling you shortly." I didn't know where that one was going. That's a good one, Ghive. Every day is going well. Space is classified by dimension? Okay. Fossils, DNA. Oh. That's kind of, yeah, that makes sense, Hamiltonian. No, this is from Winklebot, who just has an insane calculus professor, or had an insane calculus professor. I just assume that the bones have some sort of material in them that we can still recover that would be related to their genes, but maybe not. You got full points on this somehow. Verify that the series converges. Oh, so we just throw a ratio test at this bad boy. Gotta wake up in 4 hours developing robot system that build houses? Wow. Good frickin' luck, Ghive. Thank you for saying hi and for providing the dad joke. I hope you sleep well. My mind is so on vectors, I put a comma instead of a plus. Have to manhandle it? Yeah. This is very mainly math that we're doing right now. $396 to the 4n plus 1. Where did this 4 come from? Oh, that's the exponent 4. Sounds good, femvox. I guess I'll look at it after this. Yeah, it has a really big shock value, and Ramanuzan is famous for crazy-ass series like this. Okay, so this cancels with this and leaves a 4n plus 1 left over. These don't really cancel. Absolute value, everything is positive. Sounds good, Energy. Have a good night. Thank you for the question. This cancels with this, leaves an n plus 1 to the 4th left over. The real challenge, I assume, is showing this thing converges to pi. I mean, maybe that comes along with the derivation of it. I don't know. How does that interact with that? I guess we just have the 396 to the 4 left over. Now what? We have degree 2 on top, degree 4 on the bottom. So it goes to 0. So it converges? Oh, thank you. Oh, ha! I did drop that. I guess n to the 5th on the bottom then? Wait. I need this bad boy. I think it goes to 0 even harder now. Yeah. Going to 0 so hard. Yeah, not if we got matches, Winklebot. This does look like competition or JE. Log base 2 of 9. That's 3 point something. I don't think we can we relate these problems to each other? I doubt we can. They almost look kind of related, but not really. Is there a clever substitution? These are inverse functions of each other, are they not? They are. Factorial in the denominator converges. I think the factorial should go away. But yeah, that's the important bit. So what is this like? It would be like integrating x squared from 1 to 2 plus integrating 1 to... Do I have this backwards? Be 1 to 4. Wait. So like this? I think it is. And what could we say about this situation? Because I assume there's some symmetry here. Are these areas equal? I think they are. And is one of these easier to integrate? Or can we guesstimate it? I remember we talked about a few weeks ago integrals of inverse functions. I forget what exactly the thing we were doing was, but it was an idea really like this. We just need the greatest integer. Can we fudge it? Log base 2 of x cubed plus 1 is monotonically increasing. We know it's bounded above. We can bound it above and below. If we plug in x equals 1, log base 2 of 2 times 2 minus 1 is less than or equal to... log base 2 of 9, 2 minus 1. This is 1, this is 2 point something. So it depends how good of an estimate this is. 3, if I were to just guess and I had to get an answer quickly, I would guess 3. I could get tricked if the actual answer is 1 point something, though, and the answer is supposed to be 2. So the only thing we really need to show is that, like, we could even throw a series at this thing, because I don't think we can integrate either of these. But if we can just show that this integral gets above 2, we'd be home free. It's always positive, by the way. The formula for a Taylor series. I guess we're expanding around 1. Log base 2 of 2 is 1. That's an annoying derivative to take. Is there a better way I can do this? I can Wolfram Alpha it. I'm going to do that. I don't feel like getting a Taylor series by hand. Change base to E. That would be helpful. I just don't want to do that either. Because I just don't want, I'm too lazy to do it by hand. It's more like what I want. What is this bias? I got the first term right. We need to integrate this Taylor series. What log base is this? Oh, it's a natural log. So all of these terms are positive. So this is a firm lower bound. Yeah. All natural, all organic. Logs. Oh, hey, when I said my quick answer would be 3, my quick answer is actually 6. You have to multiply it by 2. Chemical logs. What I'm trying to do is I'm trying to confirm that this is 3. And I want to hope that this result is more than 2. I need a better lower bound. Yes. I think they're equal value. Choose X such as the answer is 3. Oh, I wrote 3. Maximum choice works exactly, yeah. This is a job for a calculator. Wait, no, this is more than 2. Because we have the 2 here. I'd like to say 6. Wait, less than or equal? Oh wait, less than or equal to. Ha! I was going over. Like I was saying the least integer more than. This is the greatest integer less than. So I guess 5. Final answer, Regis? You think it is 5? Question mark? Well, we can Wolfram Alpha this. Really? I wouldn't have thought that. Like to do it even with like more graphs. Or like to use the graph to get even more information out of it. I got tricked. I needed a better lower bound. I need to show it's at least 2.5 for my logic to work. You don't think they have equal areas? Really? Why not? Like, there must be a relationship, though, right? I thought that's the point of the problem. Oh, so the answer is 5. I got it by dumb luck, though. They do not have the same area. Because one is the area... Well... No, I don't get it. Maybe my mistake... I think... I drew this correctly, but the areas aren't equal. The areas that would be equal would be these two areas, I guess. You have to do the thing where you take the square that it exists in and subtract out. Steals everything feathers. Yeah, I think thinking words, thinking. Okay, what you would do is you would take you would like complete this rectangle. Get the area up here by taking the area of the rectangle minus the integral, and then add on whatever this leftover space is. Is that? Yes. Okay. Yeah, that's right, Femvox. I was trying to relate them to each other so we only have one integral to deal with. At first, I was doing that because I was hoping one of these would actually be integrable because I hadn't thought about it yet. Are they actually? Is it possible to integrate these? I don't know. Well, from Alpha gets an exact answer, so maybe it is. Um, if I take let me use the actual function. So the actual function, from what I remember, Wolfram looks something like that. And we're going when x equals 1, this function equals 1. Going like from there to there. So if I think about this rectangle here, I can say that that area is equal to log base 2 of 9 minus this integral. And then I can say this integral that work is still salvageable. Is equal to blue area plus red area. Oh. Fair enough, Pichirisu. I'm glad that you enjoyed those things. Uh, the spooky email, financial aid had to change. Pay transfer scholarship having good GPA at the old uni to nice. You love to see it. The width of this thing is 1. The height is log base 2 of 9 minus 1. Uh, Wait a second. Are we getting cancellations? $5.339. Oh my god. I was like, I was doing this in my head, and I was like, there's no way this is right. All you have to do from what I have written here is add this integral to each side. It cancels with that integral. The left side is the exact thing that we want, and the right side is something that we can plug into a calculator. Wow. That's way better than a Taylor series. That's pretty cool. Oh. Yeah. It is sneaky and beaky. That might be a closer for us. So I'm kind of tired now. Yeah, I think let's call that a closer. You know, I'm gonna be hungry soon, but whenever I stream, I kind of forget about my bodily functions. So the hunger will probably hit me once I raid out. Okay, people who are here on YouTube, thank you for being here. I'll be back on YouTube on Saturday with a normal math stream. So yeah, thank you, YouTube people.